Welcome to Late Night Chemistry with Mr. Harden. Today's episode, quick stoichiometry. Well, I've been hearing that a lot of people have been having some problem with stoichiometry. So today, what I'm here to teach you is an alternative method of doing stoichiometry. I call it quick stoichiometry. Now, alternative just means a different way of approaching and thinking about the problem. Mathematically, it's equivalent to traditional stoichiometry. So it's definitely going to work. Later on, when we start doing things like limiting reactant problems, it actually works a whole lot better and easier with that class of problems. Now, quick stoichiometry is actually stoichiometry that I do when I'm trying to figure out something quick on my calculator. So most of the time, the calculations I would do involving stoichiometry would be using this method. But when I'm working out for a class, I usually use traditional methods just because it connects with conversions and all the other things we've already done. But this will work just fine. And later on, when you add extra things to stoichiometry, we can add these extra things onto quick stoichiometry as well. So it's just going to be almost as versatile, but probably a whole lot quicker and easier. So let's get started. When we started with stoichiometry, I made an analogy to a recipe for making a BLT sandwich. 2 slices of bread plus 1 tomato slice plus 1 leaf of lettuce plus 3 strips of bacon were to make 1 BLT. And wrote it the same way that you would write a chemical reaction, because the steps to answering questions about the BLT and its process of making it were identical to what you do in a chemical reaction. So our question is, how many grams of bacon do you need to completely use up 450 grams of tomatoes? You're going to have excess amount of bread and lettuce, and you end up using all of the tomatoes to make as many BLTs as possible. Well, one way of solving it was first to go from the grams of tomatoes to figure out how many BLTs that you could make. And once you know how many BLTs, then you'd go on and figure out how many grams of bacon. Here are the steps you would work it out. Well, 450 grams of tomato, and there's 30 grams per slice. So 450 divided by 30 would give you 15 tomato slices. 15 tomato slices, you divide it by 1 tomato slice per BLT. That one's the coefficient from the reaction above. Would allow you to make 15 BLTs. Once it's on a per BLT basis, you can use that to figure out how many strips of bacon. So the 15 BLTs, and there's 3 bacon strips per BLT, that'll be 45 strips of bacon. And since each of these 45 strips of bacon has a mass of 25 grams, well, 45 strips of bacon times 25 grams per bacon strip would mean that's 1,125 grams of bacon. If you did it all together, instead of one step at a time, it would basically look like this. 450 grams of tomato divided by 30 grams of tomato per slice divided by 1. A tomato slice per BLT. That would give you the 15 BLTs. 15 BLTs will let you figure out there's 3 pieces of bacon per BLT times 3 grams of bacon per strip of bacon would ultimately give you 1125. So whether you stop at each individual step and get an answer, or just run it all together, you end up at the same spot. Well, quick stoichiometry is going to basically do the same sort of process. We're going to first do it, instead of doing anything on kind of per BLT basis, we're going to do it on the simplest basis as possible, which is the mole equivalence, which is basically just trying to find something of one of which that you can express everything else as some sort of multiple of. Now, the way you do this is you could follow this map. On this map, you'd either start with the grams of A or with moles of A, whatever information it gives you in the problem. Okay, A is not necessarily a reactant. It doesn't have to be or a product. It can be either one, because you can start anywhere and end anywhere in a stoichiometry problem. If you start with grams of whatever chemical A is, divide by the molar mass, it would give you moles of A. This is kind of equivalent to taking the grams of tomato divided by the mass of individual tomatoes to how many tomatoes. The moles refer to how many molecules of whatever substance A is. Now, once you got moles of A, or if you happen to start with moles of A, you divide by the coefficient in the chemical reaction for A. So whatever the big number is right before the whatever A happens to be is, just divide by that, and that would give you the mole equivalence. Now, I'll probably start referring to it as just equivalence from now on, but technically it is mole equivalence. Down the road, you might run into some other type of equivalence, and until then, when we talk about one type of equivalence, we can just use the word equivalence. Now, I don't have to say equivalence of what, because it doesn't matter where you start. If you divide by its molar mass and divide by the coefficient, you get the same number of equivalents. So once we're down to this mole equivalent, everything else is going to be multiplying. So the reason everything is angled down like it is because every time you're dividing, your numbers are going to get smaller. Because you always have less moles than you will have grams. You'll have less equivalents than moles. Well, they could be equal to each other, but you're never going to have any more equivalents than moles. Once you got down to the equivalence, it's as simple as possible. Everything else will be multiplying, and the numbers will be getting larger. So you multiply times whatever coefficients in front of reagent B to determine how many moles it be. And that's what the problem's asking for. You would stop there. The problem is asking for grams of something, then you'd multiply those moles by that molar mass to give you grams. So this is the quick stoichiometry map. Grams divided by molar mass will give you moles. Moles divided by the coefficient will give you moles equivalents. Equivalence times the coefficient of whatever the new thing you're looking at will give you the moles of that new thing. You multiply that moles by the molar mass, you would end up with the grams. I will also post this plan somewhere where you can print a copy for yourself. It's a very handy reference to have. Well, if we're in the classroom, I'll probably work out an example, and after that, you would work with the dry erase boards. But even online distance learning, let's work through some examples. Example 1. C3H8 is propane, so this reaction is the combustion of propane. Question: what mass of carbon dioxide is produced from the combustion of 50 grams of propane, C3H8? Well, this is a problem where you're going from grams of one thing to grams of another. So we're going to do all the steps in our quick stoichiometry plan. Our chemical A is propane, C3H8. So let's start with our first step. 50 grams of C3H8 divided by the molar mass of C3H8, which is 44.11, that's grams per mole. You'd get that by multiplying 3 carbons and adding to 8 hydrogens. So that'd be like 3 times 12.01 plus 8 times 1.01. This is molar masses from the periodic table to give you 44.11 grams per mole. You do the division, and you'd end up with 1.13 moles of propane. Step 2. Take the 1.13 moles of propane and divide by its coefficient. If, like in this case, there's no coefficient in front of it, it has an invisible 1. So you divide by the 1.13 moles of propane by 1, you end up with 1.13 equivalents. Now, once you're at equivalence, you're as simple as can be. All the steps from here on up are going to be multiplication. So, from 1.13 equivalents, multiply it times 3, it'll tell you how many moles of carbon dioxide. It's times 3 because there's a big coefficient of 3 right in front of CO2. Finally, 3.40 moles of CO2, you multiply it times its molar mass of 44.01 grams per mole. That's 12.01 for carbon plus 2 times 16.00 for oxygen to get the 44.01. You'd end up with 150 grams of CO2. Example 2. This reaction involves nitrogen triiodide. One of my favorite chemicals. Favorite because it's a very sensitive explosive. If you kind of think about it too hard, you probably make it detonate. Okay. Realistically, if you touch it with a feather, or you blow on it, you have a little random breeze, fan your hands, anything like that would be enough to cause it to detonate. And you end up with a big, beautiful purple cloud of iodine vapor. So the question is, how many moles of that purple iodine vapor are produced when 100.0 grams of nitrogen triiodide decomposes? Sorry about that. We rescued a dog over spring break, a young puppy, and doesn't seem to respect the video being recorded sign. Go ahead and continue though. So before you start, ask yourself, how many of the steps are we going to be doing? So if it's asking for how many moles of iodine, that's what we're ending up with. So moles of iodine would be, on our plan, would be moles B. The information it gives at the beginning is you have 100 grams of nitrogen triiodide. Well, that will be our grams of A. So our plan would be our grams of A is the grams of nitrogen triiodide. Okay, we're going to first convert to moles of nitrogen triiodide. Then we're going to convert to equivalents. And once we're at equivalents, we're going to convert that to moles of iodine, and that will be your ending point. So we got 1, 2, 3 steps in this problem, as opposed to 4 steps in the last example. Step 1, 100.0 grams of nitrogen triiodide divided by its molar mass of 394.71 grams of nitrogen triiodide per mole would give you 0.2534 moles nitrogen triiodide. Step 2, take that 0.2534 moles of nitrogen iodide and divide it by the coefficient in front of nitrogen triiodide. So we're dividing by 2, and that would end up giving us 0.1267 equivalents. Final step, we're going to take the 0.1267 equivalents, and since we're going to iodine, you multiply it times 3 to tell you that you have 0.3800 moles of iodine. Okay, example 3. Now, for example 3, this is what I'd like you to do. I'm going to read through the example. Once you get to the question, why don't you just pause the video and try to work it out yourself. You might need to have that printed out copy of the steps for quick stoichiometry. But here goes. The reaction is with iron 3 oxide plus carbon monoxide to make iron metal and carbon dioxide gas. Essentially what they use in the steel making process. Question is, determine the mass of iron that is produced when 12.5 moles of carbon dioxide is formed from the reduction of iron 3 oxide by carbon monoxide. So the key things is you're looking to figure out mass of iron, in other words, grams of iron, and you're starting from the information that you know you have 12.5 moles of carbon dioxide. So pause here for a minute, try to work it out, and hit resume and see how successful you were. Okay, solution time. 12.5 moles of CO2. Since we're already starting with moles, so on your plan, this would be like at moles A, you divide by the coefficient in front of, I wrote down CO2, but it is CO2. Divide by the coefficient in front of CO2, which is 3, you'd end up with 4.17 equivalents. From equivalents, everything from now on up will be just multiplying. 4.17 equivalents times 2, you would end up with 8.33 moles of iron. And finally, 8.33 moles of iron times the molar mass of iron, which is 55.85 grams of iron per mole, would leave you with 465 grams of iron. In example 4, we have a ridiculously long-looking reaction involving iron chloride reacting with potassium permanganate and hydrochloric acid to make iron 3 chloride plus potassium chloride plus manganese 2 chloride and water. Question is, how many moles of potassium permanganate, KMnO4, are needed to completely oxidize 15.0 moles of iron 2 chloride? Now, don't let the wording throw you. Completely oxidize, we can replace that with reacts. The reason we use the word oxidize here is oxidation reduction reaction. But it would be equivalent if you just said reacts with. So again, be a good time to hit pause, work through this problem, use your plan, figure out how many steps you are before you start doing it. Number one mistake I've seen when people do this is they insist on trying to make everything a 4-step problem when some things are 3-step problems or 2-step problems. And by adding extra steps, they take a right answer and make it very wrong. So figure out what you need to do first and then do it. Now, because it was only a 2-step problem, going from moles of A to equivalents to moles of B, I kind of did all in one line. So 15 moles of iron 2 chloride, FeCl2, divided by its coefficient, which in the reaction above was 5, would give you 3.00 equivalents. From that 3.00 equivalents, multiply it times 1, the coefficient in front of KMnO4, that's that invisible one, would give you 3.00 moles of potassium permanganate. So, I hope you find this useful. I will post a text version of quick stoichiometry so you can access it and see if this method of working stoichiometry problems works for you. If it makes it simpler and easier so you know what you're doing, great. If it's no better than what you've done before, then you need to contact me and maybe we can figure out a third thing. Or figure out what we need to work on with one of the existing ones to get it to work for you. Anyway, good luck. The next video will involve advanced stoichiometry, and I will show you how you can use the quick stoichiometry to make the limiting reactant problems a breeze. So, hey, thanks for tuning in to Late Night Chemistry with Mr. Harden, Episode 1, Quick Stoichiometry. Hope to see you again soon.